In this video, we're going to start looking at the tools necessary to calculate a population standard deviation or variance confidence interval. And so, first we need to establish a new type of distribution. So let's recall some of the distributions we have used in the past. So we have the normal distribution, or a standard normal distribution. Remember, that's just this bell-shaped curve. With a standard normal distribution, the mean is 0. The standard deviation is 1. It's bell-shaped and it is symmetric. So that was a standard normal distribution. We also have the student t-distribution, or the t-distribution. That distribution, it looks normal-ish. Now, I say it looks normal-ish. It has a mean t equals 0. However, it has more variability for small sample sizes. So with that normal distribution, depending on the sample size, that distribution might look a little bit different. So it might be taller or fatter. Anyway, that distribution might be a little bit different. But again, we still have this mean of 0. Still have this symmetry about the mean. It differs based on sample size. That's an important aspect of this. Now, our new distribution is the chi-squared distribution. Right? So that's a chi-squared distribution. With the chi-squared distribution, this is a distribution that is not symmetric. The values can be 0 or positive, but those values are never, ever, 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 ever going to be negative. The distribution bit is going to differ based on degrees of freedom. More degrees of freedom we have, the more normal it will be. So here's some examples of what that chi-squared distribution might look like. Right? So we could have a chi-squared distribution that looks like this red line, or like the green one. We could even have a chi-squared distribution that looks like that blue line. Right. Notice here that we have 0 is right there at that beginning, right? So that's where our 0 value is. And so our chi-squared distribution, it can differ based on these different values. Here are some degrees of freedom that give us those different curves. And notice as the degrees of freedom got bigger, the peak of that chi-squared distribution moved further to the right, and it started to look a little bit more normal-ish. Still not fully normal. It does not have symmetry. But that chi-squared distribution, that is used when we try to calculate a confidence interval for a standard deviation or for a variance. So let's talk a little bit more about those things. A confidence interval, a beta % confidence interval for a standard deviation is going to look something like this. So we have S1 is less than sigma is less than S2. We should imagine S1 and S2. These are actual numbers. So we have some number is less than our population standard deviation is less than some other number. Again, we interpret these in the same way we have interpreted confidence intervals in the past. So we think of the population parameter, the population standard deviation, as being this fixed value, and the thing that is changing is the confidence interval that we happen to obtain based on the sample that we took. Right? So we say that we are beta % confident that the interval from S1 to S2 actually does contain the true population standard deviation sigma. Recall that this is a biased estimator, but we use a sample standard deviation as the point estimate anyway. A right tail critical value is denoted by chi-squared sub r. A left tail critical value is chi squared sub L. So why do we treat these separately here, but we did not do that with either the z or the t distribution? Well, that's a good question, I think. And the answer to that is because the chi-squared distribution, that distribution is not symmetric. So for both the z and t distributions, the normal distribution and the t distribution, because of that symmetry, if we had the positive critical value, our negative critical value, the lower critical value was just the negative of our positive critical value. For degrees of freedom here, again, we are going to use one less than the sample size, just as we had with the t distribution. So we're using n minus 1, one less than the sample size. That's our degrees of freedom. If we want to use StatDisk to calculate these critical values, we are going to select analysis, probability distributions, and then chi-squared distribution. For the right critical value, we choose an area of alpha over 2. That value of alpha over 2 is based on the confidence level. Degrees of freedom is n minus 1. For the area to the right of the left critical value, the area to the right of the left critical value is actually alpha over 1 minus alpha over 2. Right? And so let me draw a quick example of a chi-squared distribution. All right, so we have this chi-squared distribution. If we're calculating a 95% confidence interval, what we're saying is we're looking at this middle area that has 95%. So that other 5% is in the two tails. And so since that other 5% is in the two tails, half of it's up here. So 0.025. So half of that 5%, remaining 5% is up there in that upper tail. And the other half, 0.025, is in this lower tail. So when we try to find this critical chi-squared value, chi-squared sub r, that critical value, it has just this area of 0.025 to the right. And when we try to find this critical chi-squared value, it has all of that middle stuff plus that other right tail. So the only thing that's not to the right of it is that, so we can take 1 minus the area to the left of it. All right, so let's go to StatDisk and we will calculate our critical values that are associated with a 95% confidence interval and a sample size of 47. So if the confidence level is 95%, then that tells us that our value of alpha is going to be 0.05. And so for chi-squared sub r, that right critical value, we have half of alpha, so 0.025 to the right. That's the area to the right of the value we want. Our sample size is 47. So since our sample size is 47, our degrees of freedom is going to be 47 minus 1, 1 less than that. So our degrees of freedom is 46. All right, so let's go to StatDisk and see what we can find. So we are going to choose analysis. We are choosing probability distributions and then the chi-square distribution. Our degrees of freedom was 46, I believe. And the area to the right of the value we want is 0.025. Let me go back and just double check this before I evaluate it. So our degrees of freedom was 46, and 0.025 is the area to the right of the value we want. And so we can evaluate this. That chi-squared value of 66.62, that is our critical chi-squared value. And to find the left chi-square value, we do almost exactly the same thing. We have the same degrees of freedom, but we have 1 minus 0.025 as the area to the right. So 0.975 to the right. So same 46 degrees of freedom, but we have 0.975 to the right of this value. And before I go over there, I am observing that this was the right critical value, and so I need to put that in the correct spot. 66.62. For that left critical value, we have 0.975 to the right of the value that we want. Still have those 46 degrees of freedom. So we evaluate that. And there we get 29.16. So again, that's right there. That chi-squared value, that is the critical value, that 29.16. So that's how we would find critical values. Once we have those critical values to come up with a confidence interval for either a standard deviation or for variance, we take 1 less than the sample size times the variance for the sample and divide that by the right critical value. Now, it might seem strange to divide by the right critical value for this left bound, but we divide by the right one because that right one will have a larger value, and when you divide by a bigger number, you actually get a smaller value. And for standard deviation, we do the same process, only we take the square roots of those two edges. So in the next video, we'll look at an example of this, and we'll walk through that using StatDisk and come up with a confidence interval for a standard deviation or a variance. We'll talk to you later. Thanks.